Today our topic continues to be the node voltage method. And this is continuation, part 2. What we're going to look at today are some special cases where we need to add some additional steps in the analysis. And the first one is when we have multiple voltage sources in our circuit. When we only had one voltage source in our circuit, we could choose one of the terminals of that voltage source to be our ground reference, 0-volt reference. And then the other terminal, automatically, we would know what the voltage would be because of the voltage drop across the voltage source. If we have 2 or more voltage sources, we generally can't do that. So we can only choose one of them, one terminal of one source, to be our reference. So this creates a wrinkle. And so let's look at that by looking at an example here. Here's a voltage source, and here's a resistor, and we'll have another resistor down here. And now here's our second voltage source, and there's another resistor like so. And then we've got another resistor up here. So these voltage source values are, let's call this one VA. Well, this will be an algebraic example just to show the method. This will be VB. And then our resistors are going to be R1, R2, R3, and R4. So solve this circuit. All right, so we get to first of all, identify all of our essential nodes, 3 or more devices connected. We got 4 of them. We can choose one to be our reference. Let's choose this one here. We could also have chosen this because that's connected to a voltage source, but let's choose that. That, of course, fixes this node to have a voltage of 0 volts relative to itself. And if we do that, of course, then this node has a voltage of VA. Okay, so that is no longer a node where we have to solve Kirchhoff's current law. And now we have remaining just 2 nodes with unknown voltages. Let's call those V1 and V2. Let's draw now all the currents through the resistors that are going to come into Kirchhoff's current law. Let's call this I1, and this we'll call I2, and I3, and I4. Now you can see the problem here. Like if we go to do the node voltage equation here at node 1, we have a current I2 plus I3 plus this current has to be equal to 0. But what's this current? Well, let's just call it IB. It's the current through this voltage source, VB. Okay, so we give it a name. And now we can say, all right, at node 1, what are our equations in terms of just the currents? Well, let's see. We're going to have here I2, I3, and IB. I2 plus I3 plus IB. Sum of all the currents flowing out of the node is equal to 0. How about at the second node where we have an unknown voltage? What are we going to get there? We get a current coming up here, which is I1, current going down there, which is I4, and then we've got IB coming in. So I1 plus I4 plus the current flowing out would be the negative of the current flowing in, so minus IB. And that's equal to 0. So there are our 2 equations. All right, that's just in terms of the currents, but of course we need to write those currents in terms of the node voltages. So we can do that by here for I1. That's 1 over R1, which we call G1, the conductance, times the voltage drop, V2 minus VA. V2 minus VA. I2 is going to be G2, 1 over R2, times the voltage drop, V1 minus VA. I3, 1 over R3, or G3, times the voltage drop V1 minus 0, so that's just V1. And I4, 1 over R4, which is G4, times V2 minus 0, so just times V2. Great, so there's I1, 2, 3, and 4, but what about IB? What is that current? Well, it's the current through a voltage source. And we don't have a formula for the current through a voltage source. The current through a voltage source is not constrained by any law directly, right? The voltage is fixed, but the current can be anything. So what do we do? Well, we could look at these equations and say, well, let's see. We could solve one of these equations for IB. For example, we could take this equation, solve for IB. So let's do that here. We could say that IB, move it to the other side, is equal to I1 plus I4. Okay? And then we could substitute that into the first equation. Okay, so what would we get then? We would get I2 plus I3 plus IB, which is I1 plus I4. That's equal to 0. So there's an equation where we know now formulas for all the currents in terms of the node voltages and the source voltages. Very well, so let's plug those in. So I2 is, this is going to be then G2. I2 is V1 minus VA plus I3, which is G3 V1, plus I1, which is G1 V2 minus VA, finally, plus I4, which is G4 V2. And that's equal to 0. And that's now an equation in terms just of the unknown voltages at the essential nodes, V1 and V2. But the problem here is, now we only have one equation, but we have two unknowns, V1 and V2. So one equation and two unknowns, we can't solve that. However, the voltage source creates a new equation. Why? Because what's the voltage drop? VB is from plus to minus, but that's V1 minus V2. So we also know that V1 minus V2 is equal to VB. So we get our equation back. So we gave up one equation to solve for IB, plugged that into the first equation, got one equation and two unknowns, but then the voltage source that created the problem in the first place gave us the solution because it gave us a new equation. So we could solve that for, say, for V2, that would be V1 minus VB, and then substitute it into this equation. And let's change the order here. Let's put the G1 over here. G1, V2 is V1 minus VB, so that's V1 minus VB minus VA. Okay, plus G2, V1 minus VA. Okay, we're getting rid of V2 and expressing it in terms of V1, plus G3, V1, plus G4, V2, but that's V1 minus VB. And that sums to 0. There we go. Now we have one equation in one unknown, V1. Everything else is known. Okay, so let's see. We could put all the V1 terms together over here on the left. And so we have G1, G2, G3, and G4 times V1. So G1 plus G2 plus G3 plus G4. And all of the other terms which have the source values. Let's see, here's a minus VA G1. Here's a minus VA G2. Put them on the other side, it becomes plus VA G1 plus G2. And let's see, down here, we've got a VB times minus VBG1, and here's a minus VBG4. Put them on the other side, it becomes plus VBG1 plus G4. And now we simply divide by this coefficient, and we have our solution for our only unknown, which is V1. That's VA G1 plus G2 plus VB G1 plus G4, and then divide that by G1 plus G2 plus G3 plus G4. Everything on the right side is known, right? The VA and VB are these voltages of those two voltage sources, and all the G's are the conductances, 1 over the resistances. Okay, and then we can solve that. Okay, now there's a way we can save ourselves a lot of steps and get the same answer, and that is to get rid of this problem current. Right, this is what caused the problem in the first place. We don't have an expression for the current through a voltage source, and we need that if that current is one of the things that comes into Kirchhoff's current law at our nodes. Well, let's create what's going to be called a supernode. We'll go like this. And it's going to completely enclose that voltage source. We'll call this a supernode. And now that current IB does not go through this surface, so it's not going to come into play in Kirchhoff's current law. Moreover, now we can right up front see this issue that we used to get our second equation before, and that is to see that V2 is actually V1 minus VB. And let me put it up on top. Oops. Okay. So that got rid of a second variable. So there was our problem of having one equation and two unknowns. So now we just have one unknown, V1, and we also only need one equation then. And this one equation will be Kirchhoff's current law for the supernode, and that does not include this unknown current. It's going to just be what? Well, here we'll have I1, here we'll have I2, I3, and I4. Well, that's this equation right here. So we directly get the equation that we ended up with after we did this solving for IB and substituting in the other equation. And then all those currents, as we already have seen, are known in terms of V1 and V2, except we could just write them directly instead of going through, first writing them in terms of V1 and V2, and then finding that V2 is V1 minus VB. We could have just written them directly here. We could say this current I2 is V1 minus VA over R2, or G2 times V1 minus VA. And this current here, I4, we could say it's V1 minus VB times G4. Okay, and that's what we got right here. G4, V1 minus VB. Right, so it just saves us the algebra to do all these steps here. They're just built into this idea of the supernode. So we just create a new node that totally encircles the two essential nodes that are connected to the voltage source. And that cuts out the current through the voltage source from entering into the Kirchhoff's current law. And then just write one equation for now, this one supernode, knowing that the two essential nodes connected to it really are defined in terms just of one unknown, in this case V1. Or we could have used V2 and then call this V2 plus VB, either way. All right, so that's the idea of a supernode. And that is going to apply whenever you have a circuit where you've got your two essential nodes that are connected by a voltage source. Let's do an example here. Here's a voltage source, resistor, another resistor, yet another resistor, and another voltage source. Resistor there. plus minus, minus plus, and then another resistor up here. And suppose we're told that this is going to be our reference here, our 0 volt reference. This is 50 volts, and this is 100 volts. And our resistance values are 20 ohms there, 24, 43, and 82. And maybe we're asked to solve for this current I flowing down through the 82 ohm resistor. Okay, how do we go about doing that? Let's see, we've already been given our reference node there. So find all of the essential nodes. Here's 1, 3 or more things, devices connected. It looks like we got 4 of them, huh? But this is 0 volts, and then we go up 50 volts from minus to plus. So this actually is 50 volts. So that's actually a known node voltage. So we don't need an equation there. Now, so it looks like we have 3 unknowns. However, notice these 2 essential nodes are connected by a voltage source. So we're going to use the supernode idea. Encircle that entire voltage source. Okay, so that we don't need to know the current through the voltage source because it doesn't go through this supernode surface. Label one of these nodes. Let's call this one V1. And then the other one, well, here we go from minus to plus, so we're going up in voltage, so this is V1 plus 100. Okay, so there's only one unknown associated with that. And then this other node here, let's call it V2, so we have 2 unknowns. Okay, so for the supernode, defined by the variable V1, let's write the equation. And what do we got? Let's see, we got the current going through the 24 ohm resistor. That's V1 minus V2 over 24. Plus the current going through the 20 ohm resistor. That's V1 minus 50 over 20. The current through, oops, down here, I'm sorry, I didn't label this was 36 ohms. We didn't have the current through the 36 ohm resistor. That's V1 plus 100 minus 0 over 36. And then finally, the current flowing out through the 82 ohm resistor. That's V1 plus 100 minus V2 over 82. So V1 plus 100 minus V2, and that sum there is equal to 0. So there's our first equation. How about at node 2? Okay, we got 3 currents flowing out, 1, 2, 3. So this is V2 minus V1 over 24. This is V2 minus quantity V1 plus 100 over 82. So let's do this. 1 over 82. V2 minus the quantity V1 plus 100. That's that. Flowing up. I'm sorry, flowing down. V2 minus V1 plus 100. And then this current here through the 43 ohm resistor, that's plus 1 over 43. V2 minus 50 over 43 that then gives you your second equation. Okay, so rearrange those into a matrix format. Let's see, first equation, all the V1 terms, 1 over 24, 1 over 20, 1 over 36, 1 over 82. 1 over 24, 1 over 20, plus 1 over 36, plus 1 over 82. Notice that is the sum of all the conductances connected to the supernode. 24, 20, 36, and 82. The inverses of those. The V2 terms, let's see, we're going to have minus 1 over 24 V2, and here minus 1 over 82 times V2. So minus 1 over 24 plus 1 over 82 times V2. All right, and then here are our unknowns, V1, V2. And the right-hand side would be all the constant terms here. Well, here we got minus 50 over 20. So that becomes, when we move it to the right, plus 50 over 20. Here we've got plus 100 over 36. That becomes minus 100 over 36. And then here's plus 100 over 82 becomes minus 100 over 82. So that's from equation at the supernode, where the variable's V1. How about at node 2? What are all the V1 terms? Here's minus 1 over 24. Here's minus 1 over 82, which is the same as this other off-diagonal term. So minus 1 over 24 plus 1 over 82. And then how about the V2 terms? We've got 1 over 24, 1 over 82, 1 over 43. So 1 over 24 plus 1 over 82 plus 1 over 43. And the constant terms, let's see, we've got here minus 100 over 82. Put it to the other side, it becomes plus 100 over 82. And here we've got minus 50 over 43. On the other side, it becomes plus 50 over 43. And there's your equation. Solve that for V1 and V2. Then you could find that I would be V2 minus quantity V1 plus 100. So V2 minus quantity V1 plus 100 over the resistance of 82 ohms. And that would be your answer. Now let's modify that previous example by adding one resistor that's going to change the way we analyze the circuit. So now we're going to have a new resistor here, 33 ohms. Here is where before we had that 36 ohm resistor. Here's our two sources. This is the 50 volt and the 100 volt source. Oops. Put these resistors in here. This is 24 ohms. Those are 43 ohm and 82 ohm resistor. And then we had this resistance up here. This was 20 ohms. And we're told to use this as our reference node. Okay, so how do we solve this circuit? We go through and we identify, well, this is 0 plus 50, so this is 50 as before. And we then look at our essential nodes. There's 1, 2, and 3. But here, these two essential nodes are no longer directly connected by a voltage source. There's now a resistor in series with that voltage source. So what do? We don't use the supernode concept, because now, remember, the supernode concept was to get around the problem that we don't know what the current is through a voltage source. We don't have a formula for that. But this voltage source is in series with a resistor, and we do have a formula for the current through a resistor. So if we solve for that current, that'll be the same as the current through this voltage source. So we don't need the supernode anymore. In fact, we don't want to use it. It's not necessary. Let's call this V1 and this V2. And now this is going to be V3. It's no longer V1 plus 100. Now V1 plus 100, that would be this voltage, right? At this non-essential node, V1 plus 100 would be right there. But this voltage, we'd have to know what this current through the 33 ohm resistor would be to figure out that voltage given the V1. All right, so what do we have in this case? Well, we just do a regular node voltage method. And we would say at V1, well, let's see. So we're going to have, we could, if we wanted to, we could maybe call this current IA. Right? And notice we can write that IA would be 1 over 33 V3 minus the quantity V1 plus 100. So we have a formula for that current, and that's the current that flows through that voltage source. So we don't have the problem of the unknown current through a voltage source anymore. So at V1, what would we have? We would have through the 24 ohm resistor V1 minus V2 over 24. So 1 over 24. V1 minus V2, because we're going this way. V1 minus V2 over 24. Yeah. And then through the 20 ohm resistor, we'd have V1 minus 50 over 20. Okay, so that's for the 20 ohm resistor. Through the 33 ohm resistor, well, that would just be the negative of this. So it'd be V1 plus 100 minus V3 over 33. So it'd be plus 1 over 33 V1 plus 100 minus V3. Okay. And that would be the three components of the currents flowing out of that node. So that'd be equal to 0. Okay, what about at node 2? Right here. Well, now here we got three currents, that, and that. Okay, so that's straightforward. This one here is V2 minus V1 over 24. So 1 over 24. V2 minus V1. And going down here, V2 minus V3 over 82. 2 minus V3 over 82. And then finally, this current going to the right, that's going to be V2 minus 50 over 43. And that's equal to 0. And then at node 3, here, okay, we have three currents, 1, 2, 3. Let's write those out. Through the 36 ohm, we got V3 minus 0 over 36. Through the 82 ohm resistor, V3 minus V2 over 82. And then through the 33 ohm resistor, that's just this IA. 1 over 33, V3 minus the quantity V1 plus 100. And that's equal to 0. So we got our three equations in three unknowns, and we could put those into vector form. So all the V1 terms here, well, it's going to be 24, 20, and 33. 24, 20, and 33. All the resistors that carry current coming out of this node. Okay, so 1 over 24 plus 1 over 20 plus 1 over 33. How about the V2 term in there? Okay, minus 1 over 24. And the V3 term would be minus 1 over 33. So minus 1 over 24 and minus 1 over 33. V1, V2, V3. And the right-hand side, where all the constants go, well, what do we got? We got minus 50 over 20 and plus 100 over 33. And those sign flips when we go to the other side. So minus 50 over 20 becomes plus 50 over 20. And plus 100 over 33 becomes minus 100 over 33. Okay? Okay, how about the second equation? What are all the V2 terms? Let's see, we've got 1 over 24, 1 over 82, 1 over 43. Those are the three resistors that are connected to that node. Okay, so that's going to be 1 over 24 plus 1 over 82 plus 1 over 43. Okay, what about the V1 term in that equation? Minus 1 over 24. And it should be symmetric, so there's minus 1 over 24. Okay, so that makes sense. And the V3 term, minus 1 over 82. Minus 1 over 82. How about the constants? Any constant? Yes, minus 50 over 43. On the other side becomes plus 50 over 43. And now the third equation. What are all the V3 terms? 1 over 36, 1 over 82, 1 over 33. So 1 over 36 plus 1 over 82 plus 1 over 33. How about V1? Minus 1 over 33, which is symmetric with that one in the upper right. Minus 1 over 33. How about V2? Minus 1 over 82, again, by symmetry. There we go. And the right-hand side, what do we got? Constants. Minus 100 over 33 on the other side becomes plus 100 over 33. So there's our system. Solve that for V1, V2, and V3. And we're all set. Now, the other special cases have to do with dependent sources. Of course, there's 4 types, right? There are voltage sources and current sources, and they can be voltage controlled or current controlled. So let's look at the current sources first. So let's look at what happens when you have a current controlled current source. All right, let's illustrate this with a circuit. And here's a resistor and another resistor. Third resistor, fourth resistor. Here's our dependent source and a fifth resistor. And we're using that as our reference. That's not much better, is it? Okay, I'll try it again. Okay, this current here is 100 IB, where IB is that current right there. This is 10 ohms. 50 ohms, 1 kilo ohm. This is 1/10 of a volt. This is 100 ohms, and this is also 1 kilo ohm. So solve this circuit using the node voltage method. So the wrinkle here is that this current source, its value depends on something else in the circuit. In this case, because it's current controlled, it depends on another current in the circuit. Well, let's first go through and identify our essential nodes. So we got the one down here, which is our reference. So that's 0. Then we got one here and one there. So let's label those as V1 and V2. Okay, so when we go through to do the equations over here at V2, we're going to have to take into account this current. And what is it? It's 100 IB. Well, what's that? Well, here's IB. So we can see that IB, in terms of the node voltages, is V1 minus V2 over 10. So 1 over 10 times V1 minus V2. And this will be 100 times that. Okay, so let's see. At node 1, we've got 3 currents, that current, and that current. So what would this be? This is V1 minus, and this is 0.1, and it's divided by 50 ohms. So 1 over 50 V1 minus 0.1 plus this current is V1 minus 0 over 1K. So 1 over 1K times V1. And then this is the current IB, which is 1 over 10, V1 minus V2. Okay, so there's our first equation. And at node 2 now, we got this current to the left, which is just the negative of IB. It's V2 minus V1 over 10. So 1/10 times V2 minus V1. And then this current through the 100 ohm resistor, that's V2 minus 0 over 100. So 1 over 100 times V2. And then this current here, which is the negative of this current controlled current source. So it's minus 100 IB. Minus 100 IB, but here's IB, which is 1/10 V1 minus V2 equals 0. All right, well, now we have two equations and two unknowns, V1 and V2, and they're, right, the IB was expressed in terms of the node voltages, and then this is just some multiple of that. And so if we want, we can now just put this into matrix form. Let's see all the things that multiply the V1 here. So this will be the G11, 1 over 50 plus 1 over 1K plus 1 over 10. 1 over 50 plus 1 over 1K plus 1 over 10. And the V2 is just minus 1/10. Minus 1/10 there. This times V1, V2. And on the right-hand side for the first equation, here's minus 0.1 over 50. On the other side becomes 0.1 over 50. Okay, so from the second equation, all the V2 terms, let's see, 1 over 10 plus 1 over 100 plus, this is 100 over 10 becomes just 10. So minus minus becomes plus 10. So this becomes 1/10 plus 100th plus 10. That's the V2 term. And then the V1, what is it? Minus 1/10. And then this is minus 100 over 10, or minus 10. So minus 1/10. And then minus 100th over 10, which is minus 10. And right-hand side, nope, no right-hand side stuff, no constants. So there's our equation. Now, notice something. This is the G matrix here. This is not symmetric. When you have dependent sources, the G matrix may no longer be symmetric. Okay, in general, will not be symmetric. So you got to be careful with that. Don't assume that you know this value because you already calculated that value. And why is that? Because this source here, this current source, its value depends on V1 through this equation. So this kind of mixes up, causes some mixing up of the equations between the two nodes. And the result is that the G matrix here, the conductance matrix, is no longer symmetric. Okay, so you can go through and solve that and get your V1 and V2, and you solve the circuit. Now let's look at a voltage-controlled current source. So let's say this is our circuit here. Resistor, another resistor. This is our ground reference. This is a supply voltage of 12 volts. Here we've got 30 kilo ohms and 10 kilo ohms. Over here is our dependent source. The resistor right here and another resistor there. This is 500 ohms and this is 50 ohms. This voltage drop from left to right, called Vx, and then this current is 10 to the minus 3 Vx. So let's solve that circuit. Okay, well, we've got, this is our reference, so that we know that's 0. We want to find our essential nodes. Well, and also, of course, this one up here is 12 volts. That's our source. So here's an essential node. There's an essential node. So let's call that V1 on the left and V2 on the right. And, of course, Vx. Vx is V1 minus V2. And now let's write our node equations at V1. So this current going up, that's V1 minus 12 over 30K. So 1 over 30K. V1 minus 12. And then to the right, V1 minus V2 over 50. So plus 1 over 50. V1 minus V2. And then going down here, V1 minus 0 over 10K. So plus 1 over 10K V1 equals 0. At node 2, over here, let's see, we got the current going down. That's V2 minus 0 over 500. So 1 over 500 V2. The current going from right to left, that's V2 minus V1 over 50. So 1 over 50 V2 minus V1. And then this current going up was the negative of that current. So that's going to be minus 10 to the minus 3 Vx. But what is that? Well, here's Vx. V1 minus V2. Okay, so minus that would be V2 minus V1 times 10 to the minus 3. So we could write this as 10 to the minus 3 times V2 minus V1. And those have to sum to 0. Those are our two equations. Okay, so let's put them in matrix format. For the first equation, all the V1 terms, let's see, we got 1 over 30K, 1 over 10K, 1 over 50. Plus 1 over 10K, plus 1 over 50. And the V2 terms is, we got a minus 1 over 50. So minus 1 over 50 there. Times V1, V2. Constant terms, let's see, we got minus 12 over 30K over on the right side. That'll become plus 12 over 30K. Go to the second equation. Let's look at all the V2 terms. We got 1 over 500, 1 over 50, and 10 to the minus 3. So 1 over 500 plus 1 over 50 plus 10 to the minus 3. And V1 terms, okay, here we got minus 1 over 50 times V1. And here we've got minus 10 to the minus 3. So minus 1 over 50, and then minus 10 to the minus 3. And there are no constant terms there, so this is 0. And those are our equations. Now, once again, notice, this is not symmetric. Generally, when you have dependent sources in a node voltage calculation, the conductance matrix will not be symmetric. So you got to keep that in mind. Okay, so then you just would solve this and plug that in. And like in this case, what you get is V1 is 0.2136 volts and V2 is 0.1950 volts. Okay, so after that, now we've just looked at the two types of current sources, controlled current sources, current controlled, voltage controlled. Then we would have current controlled and voltage controlled voltage sources. Okay, so the controlling values, right, it would be the same kinds of calculations, right? For voltage controlled, you'd have some expression having to do with other voltages in the circuit, other node voltages, and then some constant times that. So it'd be similar. And for the current controlled, it'd be straightforward, just like we did in the previous example. And the only difference then would be that this source, this controlled source, would be a voltage source. And when you have a voltage source, now the only issue is you can look and see if you have a supernode requirement. Does this voltage source end up connecting to essential nodes? And it's a voltage source connecting to essential nodes, well, then you would use the supernode concept. So you'd combine these two ideas. Now let's look at an example with a dependent voltage source. So here's an independent voltage source, resistor, 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 another resistor, and then here's our dependent voltage source, resistor, and then a current source, an independent current source. Our resistors are 10 ohm, 40 ohm, 5 ohms, 50 ohms, 100 ohms. This is 4 amps. 4 amps. This is 50 volts. And our dependent voltage source is 10 IX, where IX is that current right there. Okay, so let's solve this circuit. All right, essential nodes. There's one, there's one, there's one, and there's one. Now, this essential node is connected to this independent voltage source, and it's got a lot of components connected to it, so it makes sense to make that our voltage reference. So we can get rid of that as something we have to solve for, and that would be 0 volts. Of course, then this is 50 volts up there. Now, let's see, this current IX, well, we got to define our unknown node voltages. Now, notice here, these two essential nodes are separated by a voltage source. So we want to use the supernode idea there. We want to do this. And so let me get rid of these. We should only have 2 equations then. Let's call this V1. Let's call this V2. And then this is V2 plus 10 IX. All right, but what is IX? We look over here. Let's solve IX is equal to V2 minus V1 over 5. V2 minus V1 over 5, that's IX. So we put that into this, and what do we get? That's going to be V2 plus, so 10 times IX, 10 over 5 is 2, so that's going to be 2 times V2 minus V1. Okay, and what is that? You got 2V2 plus V2, that's 3V2 minus 2V1. Okay. So now we can go ahead and write our two node equations for this node and our supernode. So let's see, at node 1, what do we have? We got currents going to the left, down, and to the right. So to the left is V1 minus 50 over 10. So 1 over 10, V1 minus 50. Going down, V1 over 40. So 1 over 40 times V1. And to the right, it's minus Ix. It's V1 minus V2 over 5. So 1 over 5, V1 minus V2, and that is equal to 0. Now at the supernode, what are our equations? Well, we got 4 currents. This one, Ix, that one going down, this one going down, and that one going to the right. Okay, this one to the left, that's just Ix. That's V2 minus V1 over 5. Going down here, V2 minus 0 over 50. So 1 over 50 times V2. And now this current, well, this is, what is this voltage right here? We said it's 3V2 minus 2V1. That over 100. So over 100 times 3V2 minus 2V1. And then finally this current, well, it's 4 amps coming in, so it's minus 4 amps going out. And that's equal to 0. So those are our equations. Let's put them into matrix form. For the first equation, the V1 terms, we got 1 over 10, 1 over 40, 1 over 5. The V2, we've got minus 1 over 5. Okay, times V1, V2. And the constant terms, minus 50 over 10. So that becomes on the, that's, of course, 50 over 10 is just 5. So minus 5 becomes plus 5 on the right side. There we go. Second equation. Let's look at the V2 terms. We've got 1 over 5, 1 over 50, and 3 over 100. 1 over 5, 1 over 50, plus 3 over 100. 1 over 5, 1 over 50 plus 3 over 100. The V2 term, so let's see, we've got minus a fifth and minus 2 over 100, which is minus 1 over 50. So we got minus a fifth and then minus 2 over 100, or minus 1 over 50. Once again, notice that this is not a symmetric matrix. How about the any constant terms? Yes, minus 4 becomes plus 4 on the right. So there is our system of equations. And so if we solve those, we find that V1 is 64.4 volts, and V2 is, I'm sorry, V1 is, I got that backwards, V1 is 55.0 volts, and V2 is 64.4 volts. Okay, so key takeaway is when you have dependent sources, you cannot assume that your conductance matrix, the G matrix, is symmetric.